So we've just finished two sections talking about enlargements and reductions, and that leads straight into this topic, which is similar polygons. So as I've written at the top there, with similar polygons, if two polygons are considered similar, then all the interior angles must be the same, all corresponding sides must be in proportion, and what that really means is that the ratio of the lengths of corresponding sides forms a constant. Now, we could refer to that constant as the scale factor, but since we don't really have an original and an image here, we're not really talking about one being the enlargement of the other or one being a reduction of the other. We generally don't talk about scale factors. So, one thing to keep in mind is that the shape is preserved. The shape is always identical with similar polygons, but the size is different. Obviously, if you have two polygons the same size there and the same shape, then they are not only similar, but they're called congruent. In this case, all the examples we'll look at, the size is clearly different. So there's a way to symbolize this, and we can write the polygon ABCD is similar. So the symbol for similar is a little squiggle or a tilde, if you like. And in this case, we can say ABCD is similar to EFGH. Now, the labeling is actually a little bit picky here. We want to make sure that the sides that correspond to the labeling we've given, so in this case, because we wrote it as ABCD, AB refers to the short side of the rectangle on the left, and on the right, we've claimed that ABCD is similar to EFGH, so the first two letters, EF, must refer to the short side of the rectangle on the right. And, given the labeling I've got, they do. One thing I haven't talked about is how do you know that sides are corresponding? So in many polygons, especially with triangles, corresponding sides can be identified by the angle that they're opposite. So in a triangle, if a side is opposite an angle with a particular size, then the corresponding side in the other triangle opposite the angle with the same size is a corresponding side. This is obviously not helpful in a rectangle situation because all the angles are 90 degrees, and so we can't really say too much about being opposite the 90-degree angle. And even claiming that a side is opposite a particular angle is harder as well. In a triangle, it's obvious which side is opposite a particular angle, but in the case of a rectangle, it's not quite so obvious. So in the case of a rectangle, we can say, well, there's two short sides and two long sides, and so those would be the corresponding sides, or the way to identify corresponding sides. Now, the first statement at the top there says that all interior angles must be the same. But with the exception of triangles, that's not enough to have similar polygons. You can imagine taking a rectangle and lengthening one pair of sides, so in other words, making it longer and skinnier, and it's clearly still a rectangle. It clearly still has all interior angles of 90 degrees, but it's no longer the same shape. Or a more obvious example would be take a square where all four sides are the same, and then just lengthen it out and turn it into a rectangle. Again, all the interior angles are 90 degrees, but they're obviously not the same shape. So the real test for similarity is that all the corresponding sides must be in proportion. If you have that combined with the fact that all interior angles are the same, then that is sufficient. Okay, so what can we do with these similar polygons, and what kind of problems are you going to face? Well, let's say we have a couple of, let's start with some facts first. Let's say the rectangle on the left has a short side of 2, long side of 3, and the rectangle on the right has a short side of 4 and a long side of 6. So to demonstrate that the corresponding sides are in proportion, we can say, well, the ratio of the short side of the rectangle on the right to the short side of the rectangle on the left is 4 to 2. So it's 2, in other words. And that's the same as the ratio of the long side of the rectangle on the right to the long side of the rectangle on the left. So what we've shown here is that the corresponding sides are indeed in proportion. The ratio of the corresponding sides is the same. And as I said before, that ratio in the previous sections we could have referred to as a scale factor, but since we don't have an original on an image here, we usually don't talk about scale factors. Let's take a look at another example with a trapezoid. So let's say we have a trapezoid, and we have angles here. Let's say this is 60 degrees and 120 degrees, and we have a length here of 10 and a length here of 4. So let's give this a name here. We've got A, B, C, D. And let's say we have a larger version of this. So we have another trapezoid. And these angles are the same, so that's very important. If it's going to be the same shape, these angles are the same, both 90 degrees. And let's say this is a length of 15, and we want to know what this length is. And let's label this one as well, E, F, G, H. Now, if we're told that A, B, C, D is similar to E, F, G, H, we can use that information to determine the length of EH there. So we're looking for EH, and the ratio of EH to its corresponding side, 4, has to be the same as the ratio of 15 to 10. So when you're setting up these ratios for these sorts of problems, make sure that if the numerator on the left contains a side from the larger polygon, the numerator on the right must also contain a side from the larger polygon. So to solve this ratio for EH, we can multiply both sides by 4. And the 4's cancel out on the left, and we're just left with EH. And on the right, we have 15 over 10, which can be reduced, or we can just go ahead and multiply 4 times 15, which is 60, 60 over 10, which gives us 6. So EH, the length EH is 6, and that makes sense. Obviously the rectangle or the polygon on the right, everything has been increased by a factor of 3 over 2 or 1.5, and so if you multiply that by 4, you get 6. So again, these similar polygons, they're actually a little tricky to identify unless you are dealing with triangles. With triangles, it's much clearer when you have similar polygons. And in fact, most of the similar polygon questions that arise in math have to do with triangles, and that's going to be the topic of the next section.